Okay, within this MAC course, I think we're getting to the point where perhaps there's not enough information that you can easily get from the book or from Professor Miller's online content to fully grasp what we're trying to accomplish and to work through the homework. All right, so I feel like I'll add some more video explanations and you can give me some feedback and we can talk about whether this helps fill in the gaps or if I need to explain things a little further. Okay, so let's go over this homework assignment from Module 6. All right, so you're given a unity feedback system. All right, so let's talk about that for a second. Unity feedback just means there's no transfer function along this path coming back this way. So we're just literally taking the signal y of s and feeding it back with, you can think of this as having a gain of 1. When we say gain in electrical engineering, we just say we're going to multiply that signal by 1. All right, so this is a unity feedback, and it's negative feedback because of the minus sign. And ultimately, in part A, we're going to be asking for the transfer function. Okay, so let's go over that for a second. All right, so far what we've come up with is that you have an input signal, okay, make that x of t. And if you apply that to a system, all right, so we could think of this system as just a box, and maybe the overall transfer function is h of s, okay, and then on the output you get y of t. All right, so linear time invariant system theory tells you that you can find y of s to be h of s times x of s. All right, so it's Laplace transform theory. Laplace transforms turn differential equations. Okay, so we did some work on writing differential equations and turn those into transfer functions. So Laplace transforms turn differential equations into algebra. All right, so algebra is a lot easier to deal with. All right, so then we had some things where we said, all right, what if I wanted to do a step response? Well, if I did a step response, that means x of t is u of t. And once I specify the input, I can take the Laplace transform of u of t, and I know that's 1 over s. All right, so I can apply that. If I know h of s, and I know x of s is 1 over s, I can use an inverse Laplace transform to get the result. Okay, so we're talking about inputs and outputs here, and we're combining that with this closed loop transfer function. All right, so hopefully that helps a little bit. All right, so the next thing I want to talk about is let's take a look at part A. All right, so one of the things that's important and that you should just probably memorize, I have this down here, that if you have a feedback system, all right, so let me shrink this. Okay, if you have a feedback system, all right, and in general, this could be the forward transfer function. I call it forward because it goes from R all the way through to Y. Okay, and then there's the feedback transfer function, H. All right, so I think you did some work on block diagram reductions where you looked at this type of system and the transfer function between Y and R, and you can derive this, is the forward loop gain, okay, or the forward transfer function gain, which would be G, divided by 1 plus, it's plus because this is negative feedback, okay, 1 plus G times H, okay? So this is, I put some glasses here. That means you need to recognize this pattern. It's going to come up over and over in control theory, where we take this and we have a feedback path and come up with the closed loop transfer function, right? The open loop would be if we didn't have this feedback path and we just go from R through G to Y. All right, so awesome. Hopefully that helps. And let me shrink this because we'll need this in a second. Okay. All right, so now what I want to do is look at part A. And in part A, we know what, let's circle back up to here. We know what K is. K is just the gain constant. All right, so it's just a constant. And then we have this transfer function of the system. All right, so in that diagram that I gave you, or that I talked about just a second ago, this would be the G. And H would be, it's equal to 1 because there's no block that's represented in that feedback path. All right, so G is K divided by S divided by quantity S plus 2. All right, so we plug that into that formula for closed loop transfer function, and you see that's what I get here. All right, so here's the K times 1 over S plus 2. All right, then we have the 1 plus, all right, so 1 plus G. All right, remember H is equal to 1. And so we get this algebraic expression for the transfer function that we can simplify. We can multiply top and bottom by, I would simplify that by multiplying S plus 2 on both the top and the bottom. All right, so when you do that, that simplifies to this form for the closed loop transfer function. So I actually gave you that answer. No problem, we're just trying to learn here. So I'm assuming you could go back and not look at this video and be able to rederive that. All right, so the next thing you need to know is that we are taking a look at different types of transfer functions and trying to make sense of what would happen with a control system. All right, and so as you can imagine, if you have a plant or something that you're trying to control, it could be really complicated, and the linear model for it might have, lots of poles and some zeros, and it just gets complicated. So one thing we do as engineers is we try to look at some simple cases. All right, one form of a simple case is just a first order system. All right, so in that case, if it's first order, H of S would look something like omega naught over S plus omega naught. All right, just a first power of S. All right, and this could be even some kind of gain constant on the top. All right, and so we know that, in my head, I think of first order systems, and if I hit that with an impulse, hit that with a unit step. Okay, so if X of S was unit step on this input output thing that we've talked about, then I know the first order response just kind of has an exponential growth, and it tracks some constant value, why not? All right, so first order systems, sometimes that doesn't do it for giving a decent model for a more complicated system. Okay, so one of my sayings is that all models are wrong, all right, but some are useful. All right, so that comes from George Box, a statistician, and I like that idea because when we do a first order model of a system, it's not exactly right. And so the question is, how useful is it? How well does it model reality? If it models it well enough to where we can come up with a control system, then we're good. But if it doesn't, we need to look at a higher order model. And experience tells us that if we can use a second order model, that gives us a lot more flexibility in shaping the output response of a control system. Okay, so that's the next thing I want you to realize and to memorize is that a second order system, SOS, HSOS, has this form. All right, it's got omega n squared on the top, S squared plus 2 zeta omega n S plus omega n squared on the bottom. And really, I don't care so much about the top of the expression because that's just, the numerator of the expression, because that just gives you you could multiply by some gain constant and change that. All right, so what we care about is the denominator, okay? The denominator gives us the poles of the system, and by changing the locations of the poles, we can shape what the step response would be. And we care about the step response in a control system because that's how we're giving it a reference input, all right? So often you might say, okay, I want to move this robot arm to an angle theta. All right, so I just give it a, here's theta, and I try to see if the robot arm responds in the right way. Okay, so hopefully you see that. So the next thing that you need to be able to do is to, I call it pattern recognizing. All right, so you need to take a look at this denominator and identify what that would mean in the transfer function under consideration. Okay, so our transfer function under consideration is this. All right, so we look at the denominator and it's s squared plus 2s plus k. All right, so I'm going s squared plus 2s plus k, and I'm trying to match the terms. All right, so it's got a 1 out in front, that's good. And so then I look at the 2, and what I would know is that 2 zeta omega n is equal to 2. So I just equate this coefficient right here with 2. All right, and then I know that k is equal to omega n squared. All right, so from there, that gives me an idea of omega n, right? It's square root k. All right, so in the problem, he gives you a specific value of k, and that lets you compute a numerical solution for omega n. All right, and once you know omega n, you can plug that back into here and solve for zeta. Okay? All right, so what does all that mean? Well, when you start looking at second order responses, okay, if you give a step response, what we want from a step response is to eventually track to a certain reference input. All right, but we're going to have a transient, okay, and if zeta is some number bigger than 0, all right, it's going to have a little bit of overshoot in it, and then it's going to take a while to settle out. Okay, so if you look in your textbook, they give you pictures of how much overshoot there would be for different values of zeta. All right, and so your task in this homework assignment and then later on in Module 7 is to try to get a feel for what happens with different zeta values and how that affects system performance, things like rise time and settling time and overshoot. Okay? All right, so there's the basic idea. You want to relate this back to performance parameters for a step response. Okay, so I don't have these formulas memorized, but I know that overshoot, okay, overshoot, the book calls that MP. It's a function of zeta, okay? And so you can look up that formula in the book, and if you had a certain value of zeta, you can then go back and calculate the overshoot, okay? And so one of the parts up here, let's see. One of the parts asks if we're going to limit our overshoot to 10%, okay, what k value, all right, what's the limit on k that will give us no more than 10% overshoot, okay? So in general, if you look in the book, they have a table that talks about how a PID controller affects the response of a control system. In this case, this k is the P for proportional, okay? And so if you increase k, and you already had a second order dynamic system, right, increasing that gain is going to cause the system to react faster and produce more overshoot, okay? So what is the limit on k so that you restrict that overshoot to 10%, all right? So your task would be to look up that formula for MP as a function of zeta, set MP equal to 0.1, and solve for zeta. All right. Zeta then would be a function of k. All right, and you could get a limit on k. All right, it would give you an inequality, and you'd want k to be less than that number. Okay, so hopefully that makes some sense. Next, let's see. What is the rise time and the settling time for the largest allowable value of k? Again, this goes back to system performance, so read through the book, and it talks about formulas that involve the second order system parameters, zeta and omega n. Okay, so once you know a value of k, you can calculate a zeta and an omega n, and you plug into the formulas for rise time and settling time. Right, so you'll get an idea of how that works. Okay, now suppose we require that the peak time be no more than 1 second. Okay, and MP is less than 10%. So now we're adding an additional constraint on the okay, it's like peak time. Yeah, on the peak time. And there's a formula in the book for peak time. All right. And so is it possible to choose a value of k that meets both specifications? All right, and he gives you an answer here. So apparently that's part of the answer, but you know, the other part, you had a limit on k that was, you know, less than that value. And so can you meet both things at the same time is basically the question. And sometimes the answer is no, that you can't do both at the same time, and you'd have to, you know, figure out maybe a different controller or a different approach. Okay? All right, so that's the hints I have for the first part. I'll take a look at making another video for the second part.